Welcome back. In this lecture, we are going to learn the minimal amount of theory for the random graphs before we will eventually delve into the study of real-world networks. As we learned, a graph is composed of vertices and edges. Take a cocktail party, for example. The guests can be considered vertices, and the acquaintances among them edges. When the guests arrive, they tend to form isolated groups. Close friends come together and chatting, taking selfies, and so on. After some time, maybe with an icebreaker game, people mingle, change in groups, and eventually, at the end of the party, you will have a whole network of people. Then how does the resulting network look like? Before we incorporate all the realistic details related to the dynamical processes of network formation, let's start with the simplest possible but non-trivial reference model to describe a snapshot of networks in general. When we talk about random networks, two slightly different models are used equally often. The GNL model has a predefined number of vertices n and the number of edges L, which is the original version of Erdős-Rényi model. Simply put, you are supposed to link the n B's with L wires segments. So not only the number of vertices, but also the number of edges are fixed. However, the GNP model is defined with a total number of vertices n and the probability of linking an arbitrary pair of nodes p. Basically, you throw a coin, and depending on the coin flip, you can give an edge for a pair of vertices or not. By repeating these coin flips for all the vertex pairs, you construct a network. As a result, the number of edges is not constant, but a random variable. The random graph generated by GNP algorithm may produce different number of edges. This example sample random graph may be a GNL graph with 10 vertices and 8 edges. Or it may be an outcome of GNP model with 10 vertices and the linking probability of 1/6. Again, these are the three sample graphs generated by G10/1/6, which have different numbers of edges. Now, if we increase the number of vertices, you will have even more possible ways of linking individual vertices. As you see, there are some vertices with 0 degrees that are isolated from the giant component. For a bit more quantitative analysis, let's compute the probability that GNP random graph has exactly L edges. If you again remind yourself of the coin tossing problem, I guess you're familiar with the binomial distribution. Here, L max is the total number of possible pairs of vertices, and P is the same linking probability defined in the GNP model. In a GNP graph, because the linking between vertices are all independent events, the overall probability of having L links can be written like this. So the prefactor here is the number of possible ways of choosing L links out of all the L max potential links. This is a reminder of what you have learned in elementary probability theory to proceed to the degree distribution of the random graph GNP. If the random variable, small n here, denotes the number of heads out of the capital N trials of coin tossing, then it follows a binomial distribution. We are not going into the detailed derivation, but it's important to be able to express the mean and the standard deviation of the distribution in terms of the parameter n and p. From this, we can obtain the expectation number of edges, which is given like this here. One potential source of confusion is that here, in the vignette on the right-hand side, capital N itself is a number of independent trial. But the total number of vertex linking trial is not n, but L max. That is n times n minus 1 divided by 2. Variance is easily computed like this. And more importantly, the mean degree here is given by Pn if we can ignore the factor 1 for a larger scale network. It makes sense because for an individual vertex, the expectation value of degree is the linking probability times the number of all the other n minus 1 nodes except the node under consideration. In the same way, as we derived P of L, we can write down the exact probability distribution that an individual vertex has degree k, which is again the binomial distribution. Here, the prefactor is the number of possible ways of choosing k vertices out of n minus 1. P and 1 minus p to the power of k and n minus 1 minus k respectively counts the successful events of linking and n minus 1 minus k times of failed linking events. Again, the mean and standard deviation of degree distribution can be computed analytically like this. One takeaway from this is the coefficient of variation, which is the ratio of standard deviation to the mean value, is a measure of uncertainty or variability. For binomially distributed random variables, the coefficient of variation decreases as 1 over square root of n. Therefore, as we increase the network size n so that Pn square is much larger than 1, Pn square is much larger than 1 here, it is almost certain that a randomly picked vertex has the mean degree and the deviation becomes negligible. And by the law of large numbers, GNP behaves almost identical to GNL, where the total number of edges, L, is given by its expectation value. As we will see down the road, most of the empirical networks are sparse, meaning that the mean degree is way less than the total number of vertices. So within this sparse regime, where the mean degree is negligibly small compared to the total number of vertices, the binomial distribution can be approximated like this. N is the celebrated Poisson distribution. Remember, this approximation is valid when the mean degree is much less than the total number of nodes. A unique signature of Poisson distribution is that it is a single parameter distribution. We need only one parameter for a full description of the probability distribution. So the exact binomial degree distribution of random graph GNP is nicely approximated as the Poisson distribution, as long as a sparse network is concerned. In the left panel, you see a binomial distribution, which is exact. And on the right side, you see an approximate Poisson distribution, which is good enough. Here we have some sample Poisson distributions with different mean values. As the mean degree increases from 1 to 10, the overall distribution becomes more and more symmetric around the mean. If you look at the functional form of Poisson distribution, the increasing behavior below the peak is due to the exponential numerator, while it eventually turns decreasing because of the factorial in the denominator. As mentioned in the previous slide, the Poissonian approximation is good enough as long as the mean degree is much smaller than the network size, or when the linking probability P is much, much less than unity. Now let's look at the random linking process to build a GNP graph for a sufficiently large number of nodes N. When P is equal to 0, all the nodes remain isolated. Now as P increases, edges start to connect nodes, but they are still disconnected trees of typical size of log N. As we further increase the probability P, more and more nodes are connected one another, and eventually when P becomes 1 over N, a giant component is still yet to come, but there is a cluster that contains as many nodes as N to the power of 2/3. And by adding more and more edges, a single giant component emerges, to which a finite fraction of nodes now belong. The whole nodes are now more and more likely to be contained in a single component. I know this process is not rigorously defined for finite size N, and the word large or finite fraction may not sound precise, but if we imagine the limit of N going to infinity, all this story becomes precise and exact. Now, let's see how the largest cluster grows as we increase the average degree or the linking probability P. Here, the vertical axis denotes the fraction of nodes that belong to the giant component. And horizontal axis is the mean degree, or you can think it as a linking probability P. First off, for the two extreme values of P, 0 and 1, it's sort of trivial. Every node remains isolated when P equals 0, and every node is connected to every other nodes in the opposite limit. In between these two extremes, we have these graphs, both of which are also intuitively easy to understand. But how the transition occurs is not a trivial question. In fact, the transition takes place in a more or less abrupt manner at a critical value of the mean degree. And the critical value turns out to be 1. This is actually one of the major contributions made by Erdős and Rényi in their 1959 paper. But a question still remaining is, why not a gradual increase instead of the transition-like behavior? To see how the formation of the giant component follows the transition-like behavior, we first consider the fraction of the nodes U that are not part of the giant component, which is clearly 1 minus the fraction of nodes that constitute the giant component. Next, we see the same probability U, but from a node-centric perspective. If we pick a random node and consider its potential connections to all the other n minus 1 nodes, each trial for linking ends up with either a failure with probability 1 minus p, or a success with probability p. So by requiring that the random node either fails to connect to a partner node or connects to a node only when the partner node is outside the giant component, this requirement should be satisfied for all the other n minus 1 potential linking events, right? Now we see these two expressions should be actually the same. By taking logarithm on both of the on both sides of the self-consistency equation, and using the sparse network approximation, we obtain this nonlinear, actually transcendental equation. Here, S is the fraction of the nodes that constitute the giant component. As you can see easily, this equation has a trivial solution 0. If you plug the number 0 into the variable S, you see 1 minus 0 is e to the minus 0, which is okay, right? But it's a trivial solution corresponding to the case of 0 interlinking probability, where all the nodes remain isolated. So to produce the giant components, we need another non-trivial solution to this equation, which may or may not exist. Okay? To proceed further, if we set both sides of the equation equal to y, like this, we will be able to see if there is a non-trivial solution by checking the possible intersection between the diagonal line, y equals s, and the curve given by y equals 1 minus e to the minus ks. You see here that the two curves may or may not intersect, depending on the values of the mean degree. See here. Right? The criteria for the existence of non-trivial solution is that the initial slope of the curve, whether it's larger than or smaller than 1, because the diagonal line has a slope 1, right? Because this curve is monotonically increasing and convex upward, non-zero solution becomes possible if and only if this initial slope, which coincides with the mean degree, is larger than 1. You see here, right? So the initial slope of this curve should be larger than 1 to have a non-trivial solution here. And finally, the size of the giant cluster as a function of mean degree is given like this, not like the gradual increase. The further details on this transition behavior is actually a well-established topic of percolation theory in statistical physics. A connection between the emergence of the giant component and the statistical physics is the critical phenomenon, which can be observed exactly at the transition point where the mean degree becomes 1, or the linking probability equals 1 over n. A well-known example is the magnetic system. Why certain materials become magnetic, whereas others don't? The key is the alignment of spins intrinsic to electrons or nuclear particles that constitute the substance. Spins are interacting each other, and in this case of ferromagnetic interaction, an interacting spin pair has lower energy when they align each other. The spins tend to align so that the system composed of many, many interacting spins become energetically stable. At the same time, because the system as a whole may exist in lots of different microscopic configurations that share the same energy, the equilibrium material properties depend not only on the energy but also on the entropy of the configurations. Here, m is the magnetization defined as the average spin angular momentum. So it is bounded between 1 and 0. 0 means individual spins align at random direction, while m equals 1 means that all the spins are aligned to a single direction. So at high temperature, even though the alignment of spin is desirable in terms of interaction energy, the system at thermodynamic equilibrium shows a disordered spin configuration because the entropy contribution to the so-called free energy dominate the energetic cost. As we lower the temperature, entropic contribution becomes less and less important. As you see here in this expression, at low temperatures, the contribution of entropy becomes less and less important, and the spins start to align to reduce the total interaction energy, which ends up with the perfect alignment like this here. A water vapor transition or water ice transition can also be understood in a similar manner. At low temperatures, a system of H2O molecules exists as an ice crystal, but at high temperatures, the molecules show a disordered phase like water or vapor. But what happens to a system or a network exactly at the critical point? That's a whole another area of research in critical phenomena, which is not within the scope of this lecture. Instead, I'd like to point out one trivial and one non-trivial aspect of the criticality observed in the random graph. The trivial part is that each node should have one link to be connected to the giant component, right? So the mean degree 1 makes sense. However, it is a bit of surprise to see that one link per node is, in a sense, sufficient to form a giant component. And furthermore, the transition comes in an abrupt way, which physicists call phase transition. I will stop here, leaving these references for motivated physics students.